All right, we're going to take a look at quantitative chemical analysis. So we are going to do a lab of vinegar. We're going to take some commercial vinegar and we're going to determine how much acidity it actually has. Okay, so we're going to do a proper calculation for this. So what you should know is vinegar is an aqueous solution of acetic acid, essentially acetic acid in water. We call that vinegar whenever you have acetic acid dissolved in water. So how can we determine the concentration of acetic acid within the solution? Because we're not going to evaporate all the water away and leave just the acetic acid behind, because for a variety of reasons. So we've got to be able to determine any solute concentration. We have to do it somewhat cleverly. So we have to use chemical reactions and stoichiometry to do these calculations. So there's two ways we can do it. The first one is going to be the most effective, is going to be titrations, and we use these all the time. So for the acetic acid, which we have here, for the acetic acid combined with some kind of base, it's going to go through a reaction and produce a salt plus water. And ultimately, if I know how much base I'm adding, so if this is my known and the acid is my unknown, well, these two things are linked, as we've learned, because I know one molecule or one mole of base is equivalent to 1 mole of acid. So if I know when those things are finished, when I run out of acid, if I can figure out how much base I need to use, we can equate that to, well, I've used an equal amount of acid, and there we go. So how do we figure out when things are actually equal? Well, there's two ways: an endpoint and an equivalence point. They're two different things. They sound very similar. An endpoint is where you're going to use an indicator, and I'm going to show you an example of that. An endpoint is where you would see an indicator. An equivalence point is more proper. It's where you see things that are stoichiometrically equivalent. So here I have a graph of this. Here I have a titration curve, and I will say that this right here is my equivalence point. An endpoint probably would show up somewhere up here. This is mostly based on point. There we go. It's mostly based on when you see a color change, and it's a little bit off, but ultimately that's still probably going, both of these are probably going to be pretty much the same volume, right? They're pretty close to one another. So we're not too worried about that. So this volume is going to be the important volume for titration. Okay, so that's what's going to be important. So the concept is pretty simple in terms of how this is going to go. So we are going to have a burette, and the example that I'm going to show you is, so we're going to have a burette. We've done one of these before. The burette is going to contain some amount, or it's going to contain a known amount of NaOH. So I know two things. I'm going to know the volume, because I'm going to do volume final minus volume initial when I do the titration. And I'm going to know the concentration because I've standardized it, and we'll talk about standardization during the lab. Or more importantly is I've made this solution. Okay, so having made this solution makes it pretty easy. So let's see here. So yeah, so my concentration in this case, let's say, is 0.200 molar. So I've already determined that that's the proper concentration, the volume we're going to do through the titration. Okay, so I have my NaOH in this solution. I'm going to take my unknown sample of vinegar. So I'm going to have a bunch of vinegar molecules or a bunch of acetic acid molecules in here. And so here I have my vinegar. And in fact, I think the example that we're going to use, it's the similar titration curve, but the sample that I'm going to use, I'm going to have HCl. Okay, it's an unknown quantity, but I'm going to have HCl, but it's still an acid. It's still going to react pretty similarly. It's still going to react the exact same. We're still going to produce water as a result. So I know the volume of my solution. Okay, I think it's 20 mils is what I used in the video that I'm about to show you guys. But I don't know the concentration. I am unsure about what the concentration actually is. Okay, so the one thing that we do know, though, when I run this reaction, my OH minus is going to combine with my H plus, and it's going to give me water. I'm going to add an indicator as soon as I have excess OH minus, and soon as once I add extra OH minus, the solution will turn pink. Okay, so that's good. That's because I'm going to look at a solution endpoint, and this is not from a graph. This is going to be an endpoint, but it's going to be pretty close. So I know that, let's say that I end up with, I don't know, 100 base molecules before it turns pink. Okay, it just doesn't matter. It can talk about molecules, whatever, moles, but let's just say it's 100. Let's say that we actually figured out that once I add enough base, I end up with 1.2 moles of base molecule, and then it turns pink. Well, we could infer that because I used 1.2 moles of base molecules, because it's a 1-to-1 ratio, I would also have 1.2 moles of acid molecules. So those two together, so that's how I would find this concentration, is through my standardized base, or for my known quantity. Okay, again, because I know that is known, this is unknown. Okay, so let's take a look at an example of this, and I'll take some notes and we'll kind of write it down. We'll do this quick calculation to figure out what we actually have. So let me just switch it over, new share. Okay, so this is a video that I did for online labs last year because of COVID. So here we go. So here we have a standardization of an HCl. So again, we're given a solution of HCl provided. HCl becomes the secondary standard. Don't worry about that. Okay, so yeah, so we have this solution that's around 0.2 molar. So you can see I have something that is around 0.2 molar of HCl. I'm going to take some of that HCl, 20 mils. So I'm going to have a volume of 20 mils, like I had in the thing that I just finished. So I'm going to take 20 mils of this HCl, and I'm going to add it to my Erlenmeyer flask. Let me speed this up a little bit, although it's quick. So I'm going to take that 20 mils of HCl, and I'm going to add it to the flask. Okay. This is my phenolphthalein indicator. So as soon as all of this comes in, I'm going to add a couple of drops of phenolphthalein indicator. That's going to turn pink when we have reached the endpoint, or when we have an equal reaction. So I'm going to add 2 or 3 drops. Ultimately, it doesn't matter, just a couple. There we go. I'll mix it up, and I'll get my titration set up. Now remember, I have base. I have a known quantity of base in the burette here, and I have an unknown quantity. I'm going to pause it right here. So I have 2 molar NaOH in the burette. I have an unknown amount of acid below. I know I have 20 mils, but I don't know the concentration of it, because that's what we're solving for. So I have 2 molar, so I know the concentration, and we're going to figure out the volume. So my initial reading, I'm going to write this down. Volume initial, I would read that as 21, and then we're moving downward. So 21.5672. 21.82. So 21.82 milliliters. Again, this is my initial volume. So now I'm going to start the titration. Notice that it's turning pink. And because I know the concentrations are about equal, I'm going to add most of it right up front. This thing is turning pink. That's good news. And when I mix it up, they react, and it completely goes away. And again, it's exactly what I'm looking for. I'm trying to get close to that endpoint. You notice it's going away. Here we go. It hasn't completely gone away yet. Now 1 drop is going to send it from colorless, so it's to completely pink. So we have essentially reached the endpoint with 1 drop of base. I have essentially figured out where my endpoint is with 1 single drop. So I've done the titration. I'll pause this again. This is my final recording. So my volume final, again, this is of added base, is 41.1234. milliliters. Okay, so 41.40 milliliters. Good. So let's go back to our original share. There we go. So this is the information that I have. I found out that my final volume was 41.40. So let's quickly do some calculations. So this is a titration. So if I figure out the difference between those, so the volume total of, maybe I should just say the volume of base is equal to 41.40 minus 21.82. And 19.58 milliliters. So that's the volume of base that I used. Okay, we know that the concentration of base was 2 molar. Okay, so let me just highlight the things that I know. I know the concentration of base was 2 molar. We determined that the volume is going to be 19.58 milliliters. Okay, so between those two, and so here's where we know that the moles of acid is going to equal the moles of base. And so this is the big thing for solving for concentrations. So moles of base, moles of anything, by the way, when we're doing one of these concentration calculations, is going to equal concentration times volume, but the volume must be in liters because my concentration is in moles per liter. So we have to plug those in. So let's take a look at what we've got. So let me zoom out. So my concentration is 0.200. I'm going to use the full units, moles per liter, times the volume, and my volume is 0.01958 liters. Liters will cancel, leaving me with moles of base. So when I finish this calculation, I end up with 0.2, let me do the quick calculation. So 0.2 times 0.01958. My moles of base is 0.00392 moles. Okay, so that's going to be an important number. 0.00392 moles of base. So my moles of base is 0.00392 moles. But because it's a 1-to-1 ratio, I know that my moles of A, my moles of acid, are also going to be 0.00392. Okay, great. So what is, back to the original question, what was the concentration of my acid? Well, concentration, or I guess what I really should say is molarity, right? Molarity of acid is simply equal to moles of acid over volume of solution in liters. So my moles of acid are 0.00392 moles divided by the volume, and the volume was calculated because the volume was 20 mils. Let me erase this. So concentration we're looking for, we need the volume of the solution, and we did that by measuring out 20 mils in the video. So 20 mils, so 0.0200 liters. So 0.03916 divided by 0.02 liters gives me a concentration of 0.196 molar. That is the concentration of my acid. I calculated the concentration of my acid by doing a titration and getting to the end point. Okay, so that's it. It seems complicated, and the more we do them, the more it's going to make sense. Instead of coming up with gram quantities, essentially we're solving for mole quantities. So here, if 20 mils of a 3 molar solution of NaOH are required to neutralize 10 mils, so again, determine the moles here, moles of base, and we know that that is going to equal the moles of acid from this 10. We want to figure out the moles of acid And so you should be able to figure out the molarity of this solution. So ultimately what it's saying is the molarity of my acid in this case is equal to moles of acid, which is going to come from this calculation, all divided by volume of the solution. And the volume of the solution is right there. Okay, so that's a titration. The moles are equivalent in this case, moles of each. Here we have NaOH with KHP. It's the same exact thing, but instead of having a concentration or a volume calculation, we have gram quantity. So what is the molarity of the NaOH solution? Again, because it's a 1-to-1 ratio for KHP. So KHP plus NaOH yields products. Ultimately, it's a 1-to-1 ratio. So how many moles of KHP do I have? That should tell us how many moles of base I actually am going to have as well, because it's a 1-to-1 ratio. So again, this whole concept here is that we can use these things to figure out how many moles are present. From the moles present, we can figure out how many, but we have to make sure we have a balanced chemical equation. So example for 4.25, H2SO4 added to this, write out the balanced chemical equation because it's no longer 1-to-1. But again, we can still set that up. In fact, I'll start this one for you. So if I have NaOH combined with H2SO4 goes to products, again, I don't care about the products. I know I have a 2 out front here and just one of these. So what this means is I'm going to need 2 moles of OH minus is going to equal 1 mole of H2SO4 in this case. Okay, so essentially I'm going to need twice as much base as I do acid, but again, the equivalence idea is the same. And then we have gravimetric analysis. Gravimetric analysis is actually just, it's pretty much the same thing, but instead of getting a mass, we are starting with a concentration. So a solution of Ki is added to 850 mils of a 0.41 molar solution of lead nitrate. So 850 mils of a 0.41 molar solution. How many grams do we expect to precipitate out? So we have, again, we have molar quantities here and here. Those two together should give us the moles. So a solution of Ki is added to 850 mils of a 0.41 molar solution of lead nitrate. What do we end up with? So again, this is a stoichiometric problem, just starting from a different place. If we can get to grams, we're going to be okay. So how many grams of lead iodide are going to be precipitating out? So a solution of Ki, so just a ton of Ki is added to 850 mils of 0.41. So how many moles of lead do I have? That's what I'm asking you. The lead 2+ ion is going to be, again, how do we figure out moles when we're dealing with concentration? The concentration of 0.41 moles per liter, again, that's molarity, times 0.850 liters, that's going to give you moles of, in this case, lead 2+. And you can use that from there to figure out how many grams of lead iodide you have. Okay, yeah. And then same thing kind of question here and here and here. So we're going to do these in class, but that's the essential idea. Moles we're going to get, so you can get it. In fact, why don't I just finish this up? So 0.41 times 0.85. That's an L, looks like a C. You end up with 0.3485 moles of lead. Okay, so if I have 0.3485 moles of lead, well, we're going to set up a conversion. My moles of lead to, well, actually, we don't even need to do that. So there we go. So if I know how many moles of lead, I know that for every 1 mole of lead, I'm going to get 1 mole of lead iodide, right? Because this is 2 and this is 2. So for every 1 of these, I should end up with 1 of these. So another way of saying is if I have 0.3485 moles of lead, I also have 0.345 moles of lead iodide. Now let's just convert this to grams. So moles of lead iodide over grams of lead iodide. And you can do that math and we can solve it. But yeah, that's the calculation that we're doing. Same thing here. Now we have some lead iodide, we add some Ki, how many lead ions are present, what's the concentration. So again, we're doing more calculations based on number of moles. So again, it's just a conversion between different substances and moles, but it's the stoichiometric calculations that we're doing. And so we'll do a bunch of these in class, but give these a go, at least kind of look through them and see if they make any sense. All right, perfect.